of Henry's from Churchill College, who's been doing tutoring for about 5 years. He's got tremendous experience in physics and maths in particular, and studying physics at the moment at Churchill College. So you should know your onions. You've got, oh, brilliant. So we can see that screen clearly. You can see that, boys, can't you?
Mm-hmm. Yeah.
Fantastic. Can you hear them if there's any questions, Conrad? Just double checking.
Yes, yes, yes.
Wonderful. Okay.
Can we make it full screen? Below the on button. Oh, yeah. Yeah.
Yeah, we've made you full screen. Yeah. So that's phenomenal. I'm going to leave you guys basically now just to crack on. The important thing, Conrad, is you've got 2 hours, so you're going to have to give them sort of a short break every sort of half hour or so, just to keep them focused. Just a couple of minutes.
Sounds good.
And we are recording all of this as well, so we should be able to then go back and see how this works later on. Okay.
Right. Excellent.
All right. Wonderful.
Okay. Very good. Okay. So, hello guys. I am the disembodied voice in the ether. We have 2 hours, and we're going over 2 papers. So I think the general idea was that we were going to spend an hour on each paper and probably take a little break in between. However, one of these papers is or was a multiple choice paper. So I don't know, perhaps that one will take less time. We'll have to see.
Again, don't worry too much, Conrad. So I'm just leaving it now, but just do it as a trial. The important thing is to not have to worry about them getting to the stage where they're completely comfortable with it, but sort of try and get the coverage if you can, in theory. But of course, you've only got 2 hours. Normally, you have 3 hours to do 2 papers. So don't worry too much. See how far you can get. Okay.
Yep. Thank you. Okay. So, continuing. Yeah, a lot of, as you can see with the first question, a lot of the past paper, not past paper, a lot of the multiple choice paper in particular has a tendency to be quite knowledge based. It's you know it or you don't, and that's not something that I can give you a great deal of help with. It's just things that you need to know. So, for example, this first question. Pick the one with a pair of scalar and vector quantities. Well, either you're going to know that or you aren't. So I think what I would like to ask to start with this multiple choice paper is, were there any ones that you guys had particular issues with?
Keelan? There were.
Some, yeah.
Which ones?
I can't remember.
You have your paper. Wrong paper.
Yeah, it's
both.
That's not choice. What did you help me with most?
I helped you a lot on the second question. Yeah, just go through it. I don't know. I was okay with most of them.
So the second question, I didn't really understand at first.
So, sorry, when you say this, you mean just question 2, this one here?
Yeah.
Yeah. Right, yes, okay. So, all right, so this one is about SI units. So for this one, the requirement on you was to essentially know the SI units of your pressure, your acceleration, and your area and your velocity, right? Again, there's not a great deal more I can say to you about that, apart from one suggestion that I can make, which is something that I do myself. I think trying to learn all of the SI units of lots of these things can be A, difficult, and B, somewhat unnecessary. Particularly some of the things like pressure end up with some slightly bizarre SI units. I think pressure is kilograms meters to the -1, seconds to the -2, something like that. I think that sounds right. What I would suggest is essentially working out your SI units from your formulas. So, for instance, pressure. Oh, hang on. is sorry, I have a slightly dubious writing software at the moment because the main one I use has stopped working. So the handwriting is going to be slightly terrible. I apologize for that. So pressure is force over area, and that's going to give you units of newtons per square meter. And then you have, more usefully, you have force equals MA. And so you can use that to give you that your force is kilograms meters to the kilograms meters per second squared. So I would make a suggestion that, particularly if you find it a bit confusing with these ones, that working up from base equations like F equals ma and working your way through to the units is probably the best way of doing things.
Okay.
I don't know if that's a helpful suggestion to you, or what is that helpful, or what was it something else about it that didn't make sense to you particularly?
No, that's helpful.
I didn't learn SI units before, and I didn't really know how to work them out, so that's where I really struggled.
Yeah. So as I say, as far as working them out, I think the best way is to just essentially follow your way back through the equations until you find things that you do know the units of, and just kind of go from there. Most of the stuff you do will involve kilograms, meters, and seconds, because they're the easiest ones for them to find weird combinations of. So yeah. All right. So I think that one, that's probably as much as there is to say on that one. Unfortunately, there is a certain amount of just knowledge, and I think that's going to probably be a theme with this paper. Multiple choices, not the most, you don't really get weird trick things. The only thing that I did think was interesting when I had a glance through this paper was I wanted to ask you guys, as an example of sort of techniques that can make your life a bit quicker and easier. I wanted to ask you guys about what you thought of question 3 here.
I didn't really mind it.
I thought it was a bit different because when you kind of put together the formula, you usually don't put the squared outside. But I mean, I didn't find it too bad. I mean,
all right. So okay, let me ask you this. How did you find the answer to this? Did you actually calculate H and find the formula for it?
So how do I put this? How did you? So tell him. Well, you can also talk. So I took what I pretty much calculated the H by taking.
You did SUVAT, right?
Sorry?
You did SUVAT
yeah.
and stuff using the Excel. Yeah. So I would like to make a point here about this question because I thought this was interesting. And this is the sort of thing where, so I will say that's a good thing, right? And particularly in practice cases, it's useful to practice doing that sort of thing. In this case, however, it was actually unnecessary. I don't know. I wonder if this was what they were intending because of the simple fact that you can actually do this with this question. You can actually do this question by elimination and by kind of making sense of things, just from a purely instinctual perspective, right? And I thought this was an interesting thing to talk about. So what you can do instead is actually eliminate the equations A, B, C, and D by whether they make sense or not. So the first thing you can do is you can say, okay, well, naturally, it's easy to say that the faster your velocity that you throw it up at, the higher it's going to go.
Yeah.
Yep, that makes sense. So the first thing that we can say about this is that actually our equation is going to need to be proportional to V in some way, right? H is going to need to go up as V goes up rather than down.
Yeah.
And so immediately you can actually lose B and D because they have V on the bottom. And we know that it's not going to go less high if you throw it faster. That just doesn't make any sense. And then the second point that you can do, and this one's a little trickier, is a thing called dimensional analysis, where essentially you're looking at, do the dimensions make sense, right? Because if we look at A and we look at the dimensions, we have V over what is, so what type of value is G? What kind of thing is it?
It's V, right?
Sorry. So
G.
right. So what I'm asking. So G, little g for gravity.
G.
It's actually acceleration, right? That's
Yeah.
what it is. It's the acceleration under gravity. So what you've got there is a velocity divided by an acceleration, and that's actually time. So what you've got in A is an equation that says the height, which is a distance, is equal to a time, which doesn't make any sense.
No.
Whereas in C, we have V squared over A. And that is a distance. And so what you can actually do is just by looking at the equations and seeing if they make sense, you can just eliminate three of them and say, okay, well, it's C. There's no set of there's no calculations, there's no algebra to do, there's no SUVAT. You just look at them and say, well, does it make sense? And that's a thing that you can apply to a lot of cases in questions like this, where you've got a selection of equations and things. And it's a useful technique if you get used to doing it to save you a lot of time on multiple choice questions, like on multiple choice papers like this. And obviously, you know, time is pretty valuable in an exam. So I don't know, maybe that was completely bizarre to you, but I hope that that's a sort of slightly helpful thing to point out.
Yeah.
Okay, so how about now you throw me another one of the ones that you had a little more trouble with.
Okay. There you go.
Sorry. No, go.
Not just for the moment.
All right, I tell you what, if we're having trouble with that, then what we'll do is essentially I'm going to breeze through all of these questions and just very briefly note down the core points. And if there is one that you had slightly more trouble on, we can stop there and talk about it a bit more.
Yep,
So,
that sounds like a good.
For question 4, you're turning a frequency into a period. So that is just talking about either way around, really, but t equals 1 over f. Right? That's nice and simple. That's just the inverse relationship. And I mean, you have a calculator for this question, so it's really not too bad. And then it's just a matter of, you need to know that all of your, what do you call it, standard unit prefixes, that's the word. Okay, this one. So I'd like to ask you a little bit about this one, just in terms of how you understood it. So this one is combining errors. So what was the core point as you identified it for this one?
So the core point. So are you asking how we did it?
Yeah. What was the technique that you used to combine the errors?
So, well, first what I did is to get I pretty much followed in a way the PEMDAS, I guess you would call it. So first parentheses and exponents and doing that. So then t squared has an uncertainty of 1, and because it's an exponent, you would times it by the exponent, it's
Yep.
uncertainty.
Oh, that lagged out a little bit.
And then simple 4%. So you just add them and you get D.
Yeah, so that you can actually simplify this one step further. There is actually only one fundamental rule in place here, and that's that when you have fractional errors, you multiply them, you add the when essentially the simple rule is when you multiply, you add fractional errors. Hang on, let me try and actually write a reasonable plus sign here. Add when you multiply, you add the fractional errors.
Yeah.
So when you say, and this is just a useful point, but when you say, when you have an exponent, you multiply by the exponent. Well, actually, that's just because you're adding that many of them together. So here you've just got 4 plus 1 plus 1. But yeah, okay, that's enough about that one. Right, this one's a little bit weirder insofar as we've got some pictures and things. So the terminals, we have an amplitude and a frequency. Oh, right, yeah. Okay, so this one, I mean, this one isn't terribly complicated insofar as it's just about understanding how scales work essentially. Yeah, I'm not sure there's a great deal to say about this one really. Again, it comes back to the f equals 1 over t. That's the only thing. You're comparing the period, so you need that. But apart from that, there's not really much to say about that one, I suspect, that we haven't already written down. So I think we can just sort of skip over that unless there were any issues there. Number 7, we've got falling from rest. So, which statement is correct? Is there anything to say about this one particularly?
No, I think it's just that you have to kind of know the statement, and I mean, it's
Yeah,
kind
I
of
was
like
going
the
to say.
definition.
Again, so this one, there are some parts of this that are fairly obvious. Its weight decreases. Yeah. Well, that's clearly bizarre and rubbish. Yeah. Okay, cool. Let's just continue on. All right, so how many? There are 20 questions in this paper. So, right, there's a lot more to talk about, I suspect, in the other paper.
Yeah,
definitely.
Did either of you have any trouble with any of the other questions in this paper, or is it really not worth us going through and me just saying, "Oh, this seems fine" 20 more times?
I think the other paper is probably better to go through because it's written, and this one we didn't actually have too much trouble with.
Yeah, I agree. Yeah. All right, so I think what we're going to do is we're going to change our plan. We've talked about this one a little bit. That'll have to do for now. We'll move on to this other paper, to the written one.
Mm-hmm.
And I think we'll just go through this one for the rest of the time that we've got. That'll give us about an hour and a half on this one, which is the actual full amount of time. And I don't think you really needed much going over of the other one. If we have spare time at the end, we can come back to the other question paper, but I doubt that we will. Okay, so this is our written question paper. Let me find question 1. So let's start in the same position as before, except presumably there will be more to talk about this time. So what parts did you both find more difficult? And the one thing I would like to say is, can we stop using one of you as the mouthpiece and just both of you talk to me, if that's all right?
Yeah, you need to talk as well.
Sorry.
So why don't you talk for a bit, Keelan?
What are we looking for?
Sorry? What did you have trouble on?
Okay, let me just look through it quickly.
So, all right, let me phrase it this way. It's not necessarily one that you had trouble on, as insofar as you didn't get the answer. It's anything that you weren't sure about, anything that you found a little odd, any of those. Perhaps what we could do is you guys can take it in turn to suggest a question that you'd like to take a look at. I would assume that most of them are going to be towards the sort of end of each question. It's the more tricky ones that we're interested in, generally speaking.
Okay. Where did you get up to?
Sorry?
What question did you get up to?
I got up to question 5.
Okay.
Yeah.
Did you get through this? Did you have trouble with this?
I did have a bit of trouble with that. Why don't we go through this?
So, could we go through question 3B?
Sounds good. Right. That's 3B. Okay, so 3A is state Hooke's law, so this is a spring question. 3B. The variation with compression X and force F. Hooke's law. Oh, I see. Right. Yes. Okay. So first of all, I would like to point out that this question is slightly badly written, insofar as it doesn't follow on from itself very logically. So it's a slightly curious one. It's giving you the information and then asking questions that aren't related to the information it just gave you. So when it says the first part, calculate the spring constant, that's actually coming from the graph, not from any of this stuff with the tube. So calculating the spring constant, F equals kx. So your spring constant is the gradient of your graph, which is 6 in this case. 6 newtons per centimeter, so 600 newtons per meter. That seems reasonable, I think. Let me have a look. I have a mark scheme over here. So we have 3B, 600 newtons per meter. Excellent. So I'm assuming that that part was all right.
Yeah.
Yeah. So we've got, how many? Oh, wow. Got a lot of parts to this. Cool. Okay. So which parts of this were the most difficult? I'm assuming it was the later ones. Show that the work done to compress the spring by 4 centimeters is 0.48 joules. So again, presumably not too much trouble with that part?
No.
Both of you?
I part
both.
3 quite difficult.
Cool. All right, we'll start there then, properly. So the block is now released and accelerates along the tube. Okay. As the spring returns to its original length. Leaves the end of the tube with a speed of 6 meters per second. Calculate the kinetic energy of the block as it leaves the end of the tube. So again, this first bit is nice and simple, essentially. This is just E equals This is just kinetic energy, half mv squared. That part's nice and easy. So the second part is going to say, assume that all the rest of the energy is coming from your friction. So this is a more this part requires understanding. This requires a leap of logic, which without it, it doesn't matter how much maths you do, you're not going to understand what's going on here. So what we're looking at with this question is, we've said over here that in compressing the spring, we have done 0.48 joules of work. And if we have a look at our mark scheme, because we're not going to waste time on it, over here, we leave with .45 joules of kinetic energy. Okay? So what we're actually asking ourselves here is, well, where has that 0.03, I can't draw a point, there we go, joules, where has that gone? Right, that's actually what this question is about. It's saying we put X amount of energy in, and energy doesn't go anywhere. We know that. And then at that point, it's looking at the idea of doing work against a force, right? So we're then back to the original equation of, well, we're back to our equation of work equals force times distance.
Yeah.
Okay. So in this case, we know the force, in this case, we know the amount of work that we must be doing against our frictional force, and we know the distance it's traveled. So we can just find the force. Does that make sense as an approach? Which part of that did you find a struggle with?
I found that I thought the question was going to be more difficult, and I thought a lot of it was more, there would be more work in doing it.
Yeah. So one of the key points of this question to actually note is this bit, right? Average resistive force. That is the bit that says this is not a tricky question. Or, well, not a tricky question, but it's the bit that says we can use this nice simple equation, right? Because when you talk about the average resistive force acting on the block, what you mean is this is the force that we would have had if it was a constant force all the way along.
Okay.
Okay. The second point to note, just to check, is when you see resistive force, did you realize that they were talking about friction between the block and the tube as opposed to, say, the force from the spring?
Yeah. Did you?
Yeah. Okay. Yeah. So, yeah, when it says average force means this equation, right?
Okay.
This equation, because work is force times distance, only applies for a constant force. And an average force means you're treating your force as being constant. So that's why we know we can use this equation. So yeah, when you see the term average force, generally speaking, you're going to be doing some kind of work. All right, so hopefully that one seems a little bit better now that we've talked about it. Generally speaking, things tend not to be too overcomplicated at this level. And then the last one is determine the efficiency of the transfer. So that one is just a pure percentage calculation, right?
Yeah.
It's just 0.45 over 0.48. That one's nice and trivial. So yeah, I think that one should seem a little better now. So, do we want to try finding another one to have a look at?
Why don't you?
Let me just ask: Are you comfortable with that one now, or is there more that you would like to talk about?
No, I'm comfortable with it.
I'm comfortable with it now that it's for it.
Cool. Okay. So next one then. Where would you like to go?
Short end. I've already chosen last one. Short end.
I choose.
No.
Okay, so I'm kind of confused on question 7. Part
Question
C.
7.
No, not part C, part B, sorry.
Question 7.
That's right.
This paper's quite short, isn't it?
Yeah.
Okay. Okay. So,
Yeah.
this is your particles stuff.
Yeah.
So, there are 2 points that so this was one that I thought was worth talking about, but in a certain extent. So, it's a shame really, because really speaking, I feel like the particle stuff should be one of the most interesting topics on the physics syllabus, just because it's a bit weird and cool compared to, you know, putting a block in a spring and things. It's a bit more out there. But unfortunately, what it ends up being is essentially just a lot of facts to learn. So I think what we'll do is we'll just briefly go through this one in order, because it's not a very long question, actually. So, difference between a hadron and a lepton. What did you say for that?
So the difference between a hadron and a lepton, hadrons are made up of quarks and leptons aren't.
Yep. Did both of you put the same for that one?
Yeah.
Because note that this is one difference, because it's a slightly odd question to ask. It's sort of like saying state one difference between, you know, a house and a plant. It's sort of, well, yeah. Sure, I guess they're different, but they're not really related, so it seems a little strange. Yeah, hadrons, leptons are fundamental particles. Hadrons are a conglomeration of quarks. That's your kind of base there.
Yeah.
The quark composition of a proton and a neutron. Again, this is just a thing that we need, you either know or you don't, right? Proton up up down, neutron up down down.
Yeah.
That's fairly simple. Are you happy with the charges on quarks?
So
what's the charge on an up quark?
It's a positive. It's a third positive, I believe.
How about a down quark?
2/3 down, negative 2/3? No.
Try the other way around. So an up quark is plus 2/3.
Okay.
A down quark is minus 1/3.
Okay.
So
depending on the way you think more than anything else. So let me just put these in actually. So up, up, down, and up, down, down. Cool. So depending on the way that you think, it can be, for different people, easier to either remember the quark compositions from the charges or remember the charges from the quark compositions. The best one to look at is a neutron, right? So in your neutron, you have 1 up and 2 downs, and we know that the charge of a neutron is neutral, right? It's right there in the name.
Yep.
So we know that 1 up has to balance 2 downs. Yeah. And that's probably one of the best ways to remember that you've got 2/3 in the up and 1/3 in the downs.
Yeah, I get that.
So yeah, that's probably the easiest way to remember it. So now this is the only kind of vaguely interesting part. Use your answer in part 1 to determine the quark composition of an alpha particle. So this requires us to know the composition of an alpha particle. So what is an alpha particle made of?
An alpha particle would be the I believe it's the smallest. No, that's the. It's actually I'm not sure.
Okay, cool. So, sorry. Otherwise, I'm just going to start giving you names of my own. What are your names? Sorry, I have no idea.
So I'm Nils.
And I'm Keelan.
Keelan, Nils. Right, cool. So, either of you, neither of you know the composition of an alpha particle?
Doesn't it have 2 neutrons, 2 protons?
Excellent. Good. So, my first question is, why didn't you answer the first time?
Well, he knew.
But in all seriousness, because I'm just being mean, use your answer to determine the quark composition of alpha particle. So, we know that we have 2 protons and 2 neutrons. So at that point, we've just got 2 of proton, 2 of neutron. This is not a complicated question, but it's an odd one. And that's kind of what it's in there for. It's in there to try and throw you off a little bit. And it requires you to know what an alpha particle is, which you should from other things, but yeah. So our quark composition will end up being 6 and 6, which is nice and even. So part C, which I think is where you said you had the most issue, was it?
Yeah.
Yeah. So part C now is about a very specific topic, and it's one that they love to ask about. So this is the alpha particle scattering experiment. First off, we're going to ask, why is this important?
Okay.
This is a very easy question because the answer is at the top of the page, really. But why does the alpha particle scattering experiment matter? What did it tell us? Genuinely, I'm being serious. Read the first sentence of the page at me.
It's the difference between the hadron and the lepton.
Nope.
Nope.
Okay, so how about you, Kieran?
I'm not sure.
No. Okay, so alpha particle scattering experiment. It says here it provides evidence for the structure of the atom. Do you see that?
Yeah.
Yeah. So evidence for the structure of the atom. What it means is nowadays we have our little picture of an atom as, you know, you've got your nucleus and you've got your electrons sort of whizzing around it. And, you know, there's the symbol for the Big Bang Theory TV show and all the rest of it, right?
Yeah.
90 years ago, 100 probably now, an atom looked very different in the average person who knew what an atom was mind, right? Back then, an atom had this idea called a plum pudding model. And the plum pudding model was, as it suggested, they thought they looked more or less like a plum pudding. And if you've never seen one, that means it's a kind of generic sponge pudding with plums, whole plums, just sort of dotted in it. And that was what they thought atoms looked like. Because at this point, they'd discovered electrons. So they knew that those were a thing that were in atoms. But they didn't know anything more about atoms. And so they thought you had this kind of blob of atom with some electrons kind of stuck in it.
Okay.
The alpha particle scattering experiment was what said, that doesn't work. Right?
Yeah.
Right.
And this is why. So, result 1, the vast majority of alpha particles go straight through your metal foil or are deviated by very small angles. So, what can we infer from this? Well,
It's a very small particle.
That the alpha particle is a very small particle.
Yeah.
No, not particularly. I mean, so we know that all the particles we're involved with are small, but so this is an important point, right? The alpha particle scattering experiment has very little to do with alpha particles. Okay? The alpha particles in this experiment are a tool. They are not the ends, they are the means. Okay? So this experiment is all about using alpha particles to look at atoms. That's the point of this experiment. So when we're asking what can we infer, we're asking what can we infer about the atoms from the fact that these alpha particles are whizzing through. And the answer, in this case, in result 1, is the now seemingly obvious result that there's a lot of empty space there, right? So what we're looking at here is we're saying we've got this solid lump of metal and we're firing these small particles at it and they're going straight through. Now, if you imagine that we had atoms that looked like our plum pudding model, where they're this big solid blob with, you know, an electron here and an electron here and an electron here, and, you know, like this, right? This is our plum pudding model of an atom. There's one big solid blob. Well, how does an alpha particle go through that? Right? Where does it go to go through that? Well, it doesn't. Whereas in our, you know, modern model of the atom, well, it just sort of whizzes off through the empty space by here. There's nothing in the way. That's all good, right? That's fine. And so that's the big result is, okay, most of an atom is empty space.
Okay.
If most of the alpha particles are going straight through, then most routes that they can take must be empty space. So most of an atom is empty space. And that, these days, we know that. But this is where we got that from. So the first result is, let's write it down. Cool. Mostly empty. There we go. That's result 1. Result 2 is the slightly more complicated one. So, result 2, a very small minority of alpha particles are scattered through angles greater than 90 degrees. Now, take a second to think about that. When we say scattered through angles of greater than 90 degrees, what does that actually mean?
They're kind of returning, bouncing back, you know, like,
yeah,
almost.
So when you have an alpha particle going through like this, and this is its natural route, let me scroll down to give myself a little bit more space. When it goes like this, 90 degrees is off here. So greater than 90 means we're coming back somewhere over here. We have bounced backwards. So what we're doing here is we're firing an alpha particle, which is this small, dense particle, and it's bouncing back. And this also is not really what we expected, because if you go with the plum pudding model, then you've got this much, because atoms are much, much bigger than alpha particles, right? So you've got this big atom, this blob of kind of dispersed atom. And what they were expecting is that the alpha particles were just kind of going to get stuck in it. That's kind of what they were expecting to see. So there are two, unsurprisingly really, there are two results. There are two conclusions that we can draw from result 2. We know this because it's worth 2 marks. Going back to our exam technique. Have you changed anything about the setup in the last 2 minutes or so?
No.
Okay, right. I'm getting an echo of myself now, but I'll manage. It'll be fine. Okay, so two points that we want to make. The first one is, in a way, obvious, and in a way, slightly odd to grab at. We are reflecting alpha particles. What charge does an alpha particle have?
An alpha particle is a positive charge.
Yeah. So if we're going to reflect an alpha particle, what charge is it going to have to bounce off of?
A positive charge.
Yeah. So the first point that we want to make here is the nucleus is positively charged.
Yeah.
And we know that because it's bouncing alpha particles back.
Yeah.
If it wasn't positively charged, it wouldn't. So that's the big first point. The second point is this idea that you have this very small, dense nucleus. That one is, it's slightly odd. I would argue that that point about a very small, dense nucleus kind of comes from both of these in one go. But yeah, so the second point is you need to have this very small, very dense nucleus if it's going to bounce back an alpha particle, and most of your atom is going to be empty space. That one is a little bit less obvious in terms of where it comes from than the other two. But yeah, so what do we have here? We're going to have positive, small. Also, I think we're being watched at the moment, if I'm not mistaken. So, yeah. Yes, we are. Marvelous. Okay, so that's that question. That is the alpha particle experiment. It's something that you need to know about, that you need to understand, for no greater reason, really, than the fact that beyond anything else, it is one of their favorite things to ask about in A-level physics exams. They adore this experiment. I would say this question here is a pretty good summary of the most important points of it. You will get asked about this again. It's inevitable. So, yeah. Does that, generally speaking, make a fair bit more sense to you now than it did previously?
Yeah, it does to me.
Good. Is there anything about it more that you would like to ask? Anything that didn't make complete sense?
No.
All right. So, I think we will move on from that for now. As far as I gather, that was essentially the first time you'd really come across the alpha particle experiment. So I would suggest that you maybe have a look at, there's often some good diagrams and things that you can find that are much better than any I'm going to draw on the spot here. So, just have a look at it on Wikipedia or, BBC Bitesize or anything that will have some decent diagrams. It's definitely worth having a look at because it comes up a lot. So, yeah. All right. So, we are 50 minutes in. So, I think what I might suggest is that maybe, do you want to take a sort of a break for a little bit? Maybe 10 minutes until 4 o'clock? Would that sound good? And then maybe we'll go through the rest of this paper.
Yeah.
Okay.
All right. Cool. Yeah. So I think you're in a classroom, so I don't know if you want to wander away or what you'll do, but yeah. So we will reconvene at 4.
Okay. Yeah.
Cool. I will see you back here then.
Yeah.
Hey, Conrad, it's Tom here. I was watching some of that live upstairs. It was pretty good, mate. You there?
Sorry, yes, hello. Sorry, I had my mic muted for a bit while we were on the break. Good. I'm glad you were pleased with it.
Well, I could you explaining things well, and it was also coming through clearly, and the actual quality that was. I was watching it as it was being streamed, so I was watching it on YouTube, and I'm thinking it's quite remarkable in a way because you're on your iPad mirroring to your computer, which is then coming over and being streamed. And I think what's good about it is that this single stream technology that these guys use seems to work a bit more stably than sort of Google's own Hangouts on air thing. So I don't know whether they can compress things a little more efficiently, but I know Google Hangout on air isn't the most efficient way of encoding things anyway. It's just a quick encoding, but yeah, it's basically it comes through as HD, looks good, the audio is fine. You've obviously got quite a good microphone there.
Well, honestly, not really. As far as I'm aware, I'm using the microphone out of a pair of Apple headphones.
Oh, okay. Well, it's.
I mean, I know Apple headphones are pretty. Yeah. I mean, I can look into getting a better microphone if you would like.
No. Your sound is coming through quite clearly. It sounds better. Your sound is being picked up on the end feed better than the sound in the room, even though the sound in the room is rather quite good. What's quite interesting is that you are coming out. We've got one going next door, and your sound is being picked up on that one next door as well, because we've got you on quite loud here. But it's fine. It's actually good. So I'll let you talk the rest.
Quickly, more importantly, when you were watching the stream on YouTube, did you watch it all the way up to when we took the break?
I watched it. The bit that I watched was about 5 minutes around when you talked about the alpha particles and the plum pudding model and that part.
Yeah. Okay. It would be worth, if you can, having a look at just before the break, because I'm getting some feedback, as in I can hear myself from your microphone now. Yeah. And I'm not sure, but I'm slightly worried that might then be coming through on the stream itself.
Yeah. It should, if they're smart enough, it should be that should be sorted out. But let's see if I can. It's because you're coming out of the speakers on the projector. I'm not sure I can control that.
Yeah, well, I mean, the only real way to do it would be to either get a directional microphone for the classroom, or just to turn me down a bit.
Yeah. Don't worry too much about that. It wasn't noticeable when I was listening to it in the actual stream, so I'm going to assume.
It only showed up right towards the end. That was the slightly odd thing.
Okay. Well, I'll put the microphone so it's a little bit further away from the projector, and we'll see how that works. So can you hear yourself now if you speak?
Little bit, yeah. Slightly less than before, I think. But that, yeah. I mean, it's fine. I'm used to it, but I just don't want it to impact the quality too much.
It's slightly disconcerting to be able to hear yourself in the background.
Oh, it's very disconcerting. Yeah. I've got used to it over doing this and thing for a while.
Yeah. Okay. I don't think I can't control the volume here. No, it's all to do with the volume settings on the projector, which I can probably control.
Right.
But it's probably better because your volume is probably better for us to just get a directional microphone. At the moment, we've got a round table microphone, so it can pick up the voice of everybody who is in the room, which is what you normally be.
Yeah, but probably the best one to do would be to get a directional mic and just put it right in front of the projector.
Yeah.
So that the only thing you're losing is the projector.
Yeah. Okay. what I might do is I might put in, I do have a directional microphone. I may see if I can do that.
All right.
And we're just learning, I guess, we're learning that the remote ones kind of are going to work better with a directional microphone. Yeah.
Yes, I suspect so.
Let's see. I might have to. So what I'll do is I'll stop this, and then I'll just stop this, and then I will open it up again, so we can do the next bit anyway. And then I'll change mics.
Oh, okay. If you want to do that now, that's fine.
Yeah. It's fine. It's easy. I'll just stop this.
All right.
No problem.